things are going to happen.
Right. To make it simple, so you have like, I guess it doesn't matter, but so in the top left-hand corner you have a large value. Is that saying, so what I heard from what you just said is that row led to that specific value contributed a lot to the variance, or that specific what that value was first. I guess.
So an element in the matrix U corresponds with the interaction between a data point, whatever the row, and one of the singular vector directions.
Right.
And say how much of the contribution is this data point to that singular value.
Okay. I think at that point led to a higher amount of variance.
And this makes sense once you've centered first. Also.
Right.
Otherwise, you're kind of measuring with respect to the origin, and things are a little bit unintuitive. The meaning is more just a linear algebraic quantity than actually a data row.
Gotcha.
All right, I think I need to start the lecture. So great. So welcome back, everyone. So let's get started. So as many of you found out, or if you're paying attention, I told you. So I was traveling last week. So the T's covered the lectures. So from what I heard, it seemed to go okay, and they covered the material I wanted them to cover. So they did not post the videos of those lectures, so if you're looking for them, they aren't online. Although they created the material is still in the book. It followed closely. If you look at those sections in the, I labeled on the webpage for the book, it followed closely those sections, and they also created these, much more elaborate, like these Python notebooks, and just kind of walking through there will be a lot of information. So in case you missed it. Okay, and so since I'm seeing a slightly fuller room than normal, so you have realized that today is going to be the quiz. So it's going to be the quiz number 3. There was a practice quiz posted online. I guess you may have gone through it during class last week on Wednesday. Similarly, it'll be on the same topics of cross-validation, gradient descent, and it's like the PCA and it's like SVD. So the last few sections since the last quiz. And so like normal, just normal policies, remember you're going to not get any kind of electronic equipment. That's computers, phones, calculators. You can get one sheet of paper with one side of notes on it. If you haven't done that yet, you can make that now. But you won't have any other notes. And that'll be the last half an hour of class. So if it gets close to 3:45 and it looks like I'm kind of not realizing what time it is, you can give me a reminder, and I will hand them out by 3:50, and you'll have until 4:20 to finish all of the quiz. And again, like a lot of people will finish much quicker than that, but feel free to take as much time as you want till the end of the class. So, okay. So we are also now, this is also a good time as like a reminder that I highly recommend you kind of observe the lectures, right? So, a good number of you are coming to the lectures, which is great. And it looks by the numbers on YouTube, some people are watching the lectures. I'm hoping it's the ones of you who are not coming in presence of the lectures, but it could be anyone else around the world. I don't have a great way of keeping track of this. I think you'll get a lot more out of the class by listening to lectures along while you're learning the material, and I think you'll do better on the quizzes and the finals, and you'll retain, and most importantly, you'll actually retain the material better as you go on to either use this directly in what you do or adjacent to the stuff you work in, or you take in a job or in grad school, or hopefully you're taking even these more advanced classes. Like I'll be teaching the data mining class in the spring, and there's a machine learning class, and they all kind of will build directly on this material. So you'll do better if you're watching the lecture. So now that you're all, I know you're listening. That's when I'm choosing to say this. So now the other thing is we've gone through about 3/4 of the class, and we're going to start the second to last section. It's going to be on clustering. Okay, and we're going to do I think probably a fairly short 2.5 to 3 lecture section on clustering, and then we'll have 4 lectures on classification. So clustering, hopefully I'll give you a good overview of the kind of some core techniques in here. You take the data mining class, we'll see mostly, not entirely, but mostly disjoint set of techniques in clustering. It's a very broad area. There's also a graduate level class that that is also going to be offered in the spring just on clustering. That's going to cover even more breadth on just this topic. And so I think you're recommended to also have at least an algorithms class before you jump into that. But so the most kind of clustering is this area of data analysis, which is probably the least well-defined of these 4 that I put these 4 areas up on the board in the first lecture. If you remember, I put up like regression, dimensional reduction, classification, and clustering in these like 4 quadrants. Classification and regression will have this nice property that they assume every data point has a label, and so I can use this label to train something specific. I can evaluate how well I do on the label. I can use cross-validation, and there's a lot of kind of very quantifiable properties. With so dimensionality reduction, there's this kind of very clear dominant structure of the singular value decomposition, which really cuts across most of the techniques in this area. Use something related to this singular value decomposition. Not all of them, and if you take the data mining class, you'll learn about a few other ones, but most of them do. But it does not have these labels you're trying to optimize for. Clustering also does not have labels we're trying to optimize for. So it's kind of, there's not going to be a single necessarily, there's not one obvious way or one obvious kind of very closely related family of ways to kind of set up one function and try to optimize that function. And that solution, the solution to that optimum, that function will give us the answer for clustering. We will look at some ways that actually do that, but these are not at all the only ways. There are lots of variety of ways to do it. So I'll try and give some kind of vague definitions of what is the area of clustering, but kind of keep in mind that this is kind of just a kind of an attempt at kind of putting all this together. All right, so you should think of being the input is going to be a set of data, and I'll call this X. And so everything we're going to talk about in this, and so this is true in general, but what will be specific to what we talk about here is we're going to assume that this data lies in RD. This is not in general true, and in the data mining class we talk much more about some generalizations of this. Okay, we're going to assume some distance from here, and in this class we'll specifically look at that we'll use the Euclidean distance. So I'll specifically measure the distance between x1 and I'll say the distance between x1 and x2 is going to be equal just the Euclidean distance in between these points for x1, x2, in RD. Okay, so this means I'll be able to think about the points in d-dimensional Euclidean space, and in fact, for most of the class, we'll draw pictures, so it's just in 2D, so we can draw pictures of stuff. But what this lecture in particular will be trying to do is kind of give you some insights into why this is a difficult problem as I get to higher dimensions. So as d becomes more than 2, then things will become, it's less obvious how to solve the problems. But we'll give you a technique that will make intuitive sense in 2 dimensions, and will generalize the higher dimensions. Okay, so those will be the techniques we cover in this class. Okay, so the other thing you're typically given is maybe a goal number of sets, and in particular, this will be usually some value k. Okay, so I'm gonna, and it might be at the end of the last lecture, I'll talk about a technique that does not necessarily need this value k. But basically what I'm gonna do is I'm gonna try and then, well, this goal is a little bit confusing here, but just some number of sets, and then the goal is going to be to group X into K subsets. So I'm going to break this into S1, S2, up to Sk, and these are all going to be subsets of X. So the average distance between x1 and x2 is small if x1 and x2 are both in the same set. So if 2 points are in the same set, then I want the distance between them to be small. Okay? So I kind of want to find these subsets of data so that the distance between points in the same subset are going to be small with each other. Okay? So let me try and draw a picture and then say something about the picture. So now I'm going to draw a set of these points. Okay, so this would be x1, x2, x3, x4, and so on, right? So this could be my data set. This is going to be in R2. And then if I'm given a value of k equals 4, then probably what I would like to do is to kind of group them into these sets, where this set is S1, S2, S3, and S4. Okay, and so typically you want Sj and Sj prime to be to be disjoint. So that means no point is in 2 of the subsets. It's not a strict requirement, and we will see versions where this is not true. But this would be called hard clustering. Yeah.
So we're not necessarily forming a partition of X. That's not always the goal.
In hard clustering, you are finding a a partition events.
Okay.
Yeah, so it's actually going to be a partition. I also want every data point to be in one of these things. That's typically the goal. That's not always the goal. Sometimes you say, I want to allow some outliers, which I don't put in a cluster, and I either want to explicitly identify them, or I don't necessarily need to, and there's all sorts of these variations. Okay, but in what we talk about in this class, every point will be assigned somewhere. We're not going to get into dealing with outliers or types of formulations where we kind of just think about things that aren't a partition or that don't assign some points and don't label them outliers. But,
Is K kind of like a hyperparameter, or is it or not?
see, yeah, so usually when you, I mean, it is kind of like a hyperparameter, but usually when you use that term, it's in the context of like optimization, and then you might be able to tune K, but it's going to be harder to set up an optimization problem here, right? I'm not going to have necessarily a single cost function, which I'm going to then optimize the cost function. It turns out we're going to do that, but that's not going to give us any means at all, even with cross-validation, to tune K. We're going to have to use more ad hoc techniques to kind of choose K. So similar to like doing dimensional reduction with PCA, how many dimensional subspace is good to choose, right? There's not like a single easy great answer for that either. And you need to kind of do ad hoc, or whatever seems to help you understand the data is the right answer. And then I might mention some tricks you can use to help you choose K. But often it's given as input, right? For here, what I've described here, I'm giving this as input, right? This is the input, and this is some formulation of the goal. Some vague way of saying the goal. Okay. Okay, before I say anything about techniques, yeah, so, how did I solve this problem? I drew the points on the board, or I could have plotted them in 2 dimensions if they're 2-dimensional, and I assumed Euclidean distance and all that stuff. If I didn't assume Euclidean distance, I can use MDS to draw them in 2 dimensions, right? So we have other tools to get us here. But now that I've drawn them in 2 dimensions, and I want 4 circles, how did I solve this problem? Like, what did I do to solve this?
You look at it, and it looks like there's 4 clusters.
Yeah, that's actually what I did, and this is actually the algorithm I would recommend you to do if you have 2-dimensional data points and you're clustering it. I'm not kidding. Okay, I don't recommend you try and run something necessarily out of the box. If you can plot them in 2 dimensions, plot them and circle them. Otherwise we're gonna be forcing some mathematical formulation on here, and there's not one obvious mathematical formulation. There's like a variety of them. It's not clear which one is better until you run them, and then maybe it does something automatically. But if you're gonna run them and then plot them and then look to see how well it did, you might as well just circle the points to start with. Sounds kind of odd, but okay. So we're going to give you some mathematical formulations that are based on like, okay, these are generated by Gaussians or something like that, and we'll walk through those, and that might be a good choice. But it's not a bad idea to plot them and circle them. Okay. Okay. I'm going to tell you basically very briefly the kind of essentially the family of things we're going to be doing are going to be looking at these clusters based on centers. So center-based clustering. And so what this basically does is, in addition to these kind of circles, it's going to identify these points which are centers. They may or may not be points in the data. So I'll call this C1, C2, C3, and C4. Okay, and then I can use these points as a proxy or like as a model that represents this data. Okay, so now I can say if I'm gonna assign all the points of this cluster which are closer to C1 than they are to anything else. Okay, so and to C4, if they're closer to C4 than they are anything else. And there's a family of clustering techniques. The most common is the kind of version of this, and we'll define this on Wednesday, is going to be called k-means. Okay, and this is a problem formulation, and we'll walk through the most common algorithm called Lloyd's algorithm for for k-means. Okay, so that'll be the focus of Wednesday's lecture. Yeah.
For those centers, are they just the average x and the average y values?
They could be, but it depends on the formulation. And if you do k-means, that'll be a good choice. But if you do k-center or k-medioid or k-medians, that's not going to be a good. That may not be a good choice. May not be the right choice. And if you're not in Euclidean space, that average may not be something that's well defined, actually. And so in the data mining class, we say, well, what if you're not in Euclidean case? And we'll motivate this. By the time we get to this lecture, you'll see examples where you don't want to use Euclidean distance, and you won't be able to do that. Okay, so this becomes kind of a right. Okay, but for now we'll just describe this as, these are points which are they're representative of the clusters. Okay, and we'll talk about specifically what the k-means formulation means on Wednesday. What I think is most interesting that we're going to talk about now, and I think this is really, I think this formulation is pretty essential for understanding, kind of conceptually understanding what's going on with k-means, but really any center-based clustering, is I said something in words that describes some mathematical structure called the Voronoi diagram, and we're going to talk about that the rest of the lecture up until the quiz. Okay, so let me try to draw this picture, and then we'll mathematically define it, and this will provide us the foundation for understanding kind of the k-means and k-center-based clustering algorithms, and also how Lloyd's algorithm works. So I'm drawing some lines here, and these lines are called the Voronoi diagram. Okay, so these lines are called the Voronoi diagram, and these kind of extend up to infinity in these structures. And what I've done is I've kind of decomposed the R2 here, the plane, the whiteboard, into 4 regions. Initially, I just drew these blue circles, right? These blue kind of, that contain all the points. But I've actually divided it so that if I have some other points, I can, I know which cluster it belongs to, right? Basically, everything in this region here is going to be everything that's assigned to C4. Everything in this region is assigned to C1 and so forth. Okay, so I'm going to look more carefully at. So I'm going to start with a set of, I'm going to call these today sites. Okay, this will be, and these are like the centers here, but this is going to be S1, S2, up to SK, and these will be points in RD. Okay, so these are the points here. These are the red center points. This is equal to C1, C2 up to CK. Okay, and then I'm going to define a function. Let me write this function on the board. Oh, this is R. And let's look at what this function means. Okay, so this function is going to return for any point x, right? So now one of the black points, or any one of those points, can be a point x in the plane. It's going to map it to one of the sites. Okay, so every point in the plane gets mapped to one of the sites. It's going to be argmin over the set. So if you remember what the argmin is, the argument of the set I'm considering, the set of sites, that minimizes this function value. In this case, the function value is going to be the distance from a point x. Okay, so if I have a point, kind of a potential point x here, I can think of the distance from this point, and this is like a cone coming out, and I want the element of one of my sites which minimizes this cost. And this sets are going to be, it's finite, so I can just evaluate this for each of, I can evaluate this for each of the sites if I want to. Right, so I can just evaluate the distance for each of the sites, and I'm going to return the site which is the minimum. Okay, and this gives me the assignment of any point x onto a cluster center, is what it's doing. Okay, but this is also describing this like Born diagram, and it's kind of decomposing the plane, and every point is mapped to a different center, but this has these nice shapes to it. In this case, they're at least still pretty nice. They're kind of these convex shapes, and these are convex. Any kind of 2 points I can connect by a straight line, just like we define, similar to how we define convexity when we were dealing with functions. And so it's going to have these nice structures. It's going to be defined by these line segments, in fact. Okay, and so this function and this Born diagram, which corresponds to it, is really going to kind of tell you a lot about the structure of any center-based clustering, or any assignment-based clustering, where the clustering is defined by centers. It doesn't matter how I choose the centers, but in this formulation, I always assign a point to the closest center. So it always follows this underlying structure here. So to understand any of these clustering algorithms, we need to kind of understand how do we draw these like Born diagrams, which is just the structure underlying this function here. Okay, so this function itself makes sense? What this is doing?
Just on the last, we haven't yet defined how to find a specific site or how to break up.
Yeah. So what will be on Wednesday is how to define the sites, and we'll pick one way of saying this is what the optimal sites property they would have, and then we'll look at some algorithms for doing that. But for now, I want to kind of give you a sense of underlying structure, so it'll be easier to describe these algorithms. Yeah. Right. So okay. So one property this has is it's going to define a region Rj, which is going to be, again, the set of points in Rd, and the d-dimension Euclidean space, such that the distance from x to Sj is going to be less than or equal to x minus S I for all I not equal to j. Okay? So a region, and so this region might correspond to, for now the region R3 is going to be all of these points here, right? It's a subset of the plane where all the points here are closer to C3 or S3 in this notation than they are to any other center, right? And so these are what these regions of the Voronoi diagram are. Okay. And so now I kind of want to spend a few minutes convincing you that the structure is simple, that this is going to be made of edges and vertices that kind of defines a graph, and these will be kind of these straight line edges. Okay, and then start to say, okay, it's got a nice structure. Can we use this in clustering? And then I'll kind of give you some bad news. But in order to really make the bad news convincing, I need to kind of emphasize that this is this structure is like really at the core tied to what clustering is doing. Okay, so we can also define, and so a region has one value, j. I can define an edge eij, okay, and this is now going to be this set of points in Rd such that x minus Sj is equal to x minus Si, and this is less than or equal to x minus Sl for all L not equal to Ij. Okay, so again, this edge is going to be a subset of the plane, but if I look at an edge here, this would be E2, 4, right? It's all the points along this edge. They're equal distance to these 2 points, and they're less than the distance to either here, right? So it's going to end at some points, these vertices here. Okay, so all these points are equal distance, and to convince you that this points are exactly the the bisector between C2 and C4, and a bisector is going to be a straight line. Okay, it's going to have this property that if I draw, this is E, say 2, 4, this is going to be S2 and S4, then it's going to be the bisector between these two sites. And if I picked any point X, then this nice property that if I draw a circle that is centered here at X, and it goes through S2, it will also go through S4, that this distance is equal, right? The distance S2 is equal to S4, and this is going to be, this bisector is going to be a line, because I can basically decompose this into this, using the Pythagorean theorem, into the distance of the length of the projection onto the line and the lateral movement along here, right? It's this squared distance is the sum of these two squared distances. Okay, so this allows me to kind of say it has to be on this line, all these points on this edge. Okay, so it has this nice linear structure. For instance, if I replace the points S2 and S4 with more complex objects, which people have studied, this is no longer necessarily a linear structure. So it's not kind of inherent, it has to be that. So it's nice that this occurs. And then basically a vertex happens. Then you also get this vertex, and Vij L is going to be X in Rd, such that X minus Sj equals to X minus Si equals x minus SL, and this is less than or equal to x minus SR for all r not equal to IJL. Okay, so this is now 3 points, and this basically happens when there's some other point over, let's say it's over, this is say SL, and I'm sliding this point along this line, and the circle is growing as I do it until the circle hits here, until it hits this other point. What's going to happen now is the circle will look like this instead, and this point is going to be V2 for L. I guess I've mixed numbers and variables, but that should be okay. Right, so now I've got this vertex, which is the center of this circle, and this circle contains no other points. Okay, so this is how we define this vertex. Okay, and so should be a special point. If I pick 3 points and I try and draw the smallest enclosing circle of 3 points, it should touch all 3 points unless it could either touch 2 or 3 points. I could also have the smallest enclosing circle might look like this, 2 antipodal points, but this case is kind of this one will not generate a vertex because this one won't ever happen in the diagram because this point would need to be equidistant. So this one does not actually occur in the diagram. Okay, so you can draw this. You can construct this. It has these properties that is defined by these empty circles that have 3 points on their boundary to find these vertices. Okay. Okay, good. So let me say a little bit about the size complexity. Switch markers. Okay, so in R2, in 2 dimension, I can say the number of regions plus the number of edges plus the number of vertices is something less than something like 6 times k. There's some constant in front here. There's some small additive term. Basically, the complexity of this grows linearly with the size of the sites. So I can define, like the vertices are defined by triples. So you might think there might be kind of k cubed of these, and these are defined by pairs, so there might be k squared of these. But the total complexity is linear in R2.
Are you talking about like algorithmic?
I'm not talking about how to compute it. You can compute it
Or what are you mean by complexity?
just the size, the number. I can put down any set of k points, any set of k sites, not all vertices appear, not all edges appear. Turns out the total number of regions, number of regions is at most k, right? The number of edges is actually about 2k, and the number of vertices is about 3k. So there aren't that, or maybe the number of vertices is also about k, and this is about 4k. But it's basically the complexity of this isn't that big, and turns out there are algorithms to compute it, which run in linear time in k, or near linear time with like k log k, right? So I can compute this, and this tells me how to always find the closest point just by this diagram. And in the plane, I can actually build something like a binary search tree on top of this that assigns x to the closest point in roughly log k time once I've built this. Okay, so this is actually pretty cool. I can generalize binary search to find the nearest point to 2D using this Mornay diagram. Yeah?
You said the number of regions at both K. How could it be not K?
So, I mean, it could be that a region is, for instance, I should say faces, and the region might not be connected even. You can imagine there are versions of this where I play around with Euclidean distance or different distance, and the regions aren't actually connected. But I'm just saying the total complexity of describing this in a data structure is linear in K. Okay. And so in order to define kind of center-based clustering, in order to define the best location of these sites, which I'll want to do, I need to kind of understand how to assign data points onto these sites once I've chosen an example site. And in 2D, this actually has a lot of nice structure. Okay, so the bad news about this is in RD, the size, complexity, number of regions, edges, vertices. In fact, there are more complex objects that appear as well. You get these kind of these two-dimensional subfaces and so forth. That this you can think of generalizing these things to have one thing be the least, two things be the least, three things, and four things, and so forth. But the total size is now going to be O of K to the power of the floor of D over 2. Okay, so so it's this ceiling. Sorry, the ceiling of D over 2, which means that when D is equal to, so when D equals to 1 and 2, this is going to be O of K. When D equals 3 and 4, this is going to be O of K squared. When D equals 5 and 6, this is going to be O of K cubed. And, you know, in 3D, sometimes with some nice data, it's actually closer to linear. But already in 4D, this is going to be kind of roughly K squared. And it grows exponentially with dimensions. And we're going to have data that's in higher dimensions, and which basically means we do not want to construct this. The alternative to using this is for every data point, just check all the K distances. And so that's going to be easier to compute. So this structure is not going to help us in higher dimensions. It'll be really useful for understanding k-means clustering in 2D, to understand what's going on. And that structure is still there, but we're not going to be able to compute it anymore to help us. Okay, and we're not going to be able to search over these structures. It's going to make the problem really hard and messy in higher dimensions. So we'll get intuition in 2D, but we'll not be able to use that computationally in higher dimensions. Yeah.
Could you still construct a binary tree to, like, let's say that you cared most about computation and putting people in these clusters quickly, once you already have a cluster.
Yeah.
Could you then use like a binary tree in the same way to put people like quickly, basically like put new people that are coming into your cluster?
Yeah. So you're asking about kind of faster nearest neighbor searching in higher dimensions or for other sorts of distances. And there's an entire chapter in the textbook about this. Okay. And it's a really fascinating topic. We spend time on this in the data mining class. We are not going to have time to go on any depth in this class, but it's a really cool topic. Yeah. So you can do some stuff like this, and actually, from like theory perspective, this really developed around 20 years ago. But from a software perspective, this has really become mature in the last 5 years or so. So now there's some really cool software online that actually works in Euclidean high dimensions actually really well. For other sort of distances, sometimes there's some stuff that works, and sometimes we don't really have any clue, and it's known to be hard. And these are some of the things we'll discuss in the data mining class. Yeah, that's a good question. You have a question too, or is this the same thing? Okay, good. So this is known as an example of like the curse of dimensionality. Okay, so if you've heard of the curse of dimensionality, maybe. Example where things that kind of are simple and look nice and well behaved in low dimensions, when you get to high dimensions, the complexity blows up and it grows exponentially in the dimension. It grows exponentially in the dimension. And things that you thought would work in low dimensions kind of just start becoming infeasible in high dimensions. And so, a lot of the day mind class will be talking about ways to get around the curse of dimensionality for places where it comes up, and this is one of those cases. Okay. I'll say one more thing very, very quickly. There's this, just so you mention it, and then we'll break for the quiz. There's some dual structure, which is really cool, called the Delaunay triangulation. Okay, and this is what's called a triangulation on the point set, and it's basically a way of, in 2D, but this generalizes to high dimensions in the same way, that turns kind of, I kind of connect all the points with triangles, but the edges don't cross. Right, so in 2D, you're getting a planar graph, and it's a very special planar graph. It's the one that maximizes the minimum angle, for instance. So it has a bunch of really nice properties, and in graphics, it's kind of like the default way of triangulating. It creates like tetrahedral meshes in 3D, and it's a generalization. And so it turns out it's an exact dual of the Voronoi diagram, in that every region corresponds with a point, like a point. Every edge corresponds with an edge. This green edge corresponds with this purple edge, and every face in the triangulation corresponds with a vertex in the Voronoi diagram. So these regions, edges, and vertices kind of correspond with kind of one-to-one with an object in the Delaunay triangulation. So the size complexity of the Delaunay triangulation is the same as that of the Voronoi diagram. And this is like a super important tool in computer graphics, and kind of allows you to find kind of, if I want to interpolate the function value from these kind of the other points around, the Delaunay triangulation tells me which points to interpolate the value from, for instance. And that's one place that shows up in data analysis. There's a little bit more details in the book, but I think I'll stop here. This is kind of a cool, short kind of segue into some geometry and Delaunay. Okay, so we'll use this on Wednesday to discuss k-means clustering, and then I think we'll look at mixtures of Gaussians after that. Okay, so for the quiz, okay, so we'll hand out the quiz in just a second here.